Now, when resistors are connected in series, okay, conventionally, current always flows from the positive and then enters into the negative. When resistors are connected in series, the current flowing through each one of the resistors is the same. Same current will flow through all of them. So when resistors or loads are connected in series, same current flows through all the resistors. But potential difference across the resistors vary. So it is similar to this scenario. The resistance of R1 is different from R2. But you have same current flowing through all the loops. Okay. So it is like you may eat so much, but because you are connected in series, you'll be given equal food no matter your food intake. Food deeper and so obisu nidi, but you get the same amount of food. This is because of the series connection. And the same current flowing through all of them is due to the fact that there is no junction in this. There is no junction in series circuits. There is no junction. Or mesh. This is the reason why same current flows through all of them. In electricals, please, are you there? Are you following?
Yes, please.
In electricals, when we talk about a junction, it is a point where 3 or more wires connect. A junction refers to a point where 3 or more wires connect. Okay, so look at this point. Over here, we have this wire and this wire. It's not up to 3. Over here, we have this wire and this wire. It's not up to 3. Here and here, the same. So the same amount of current flows through all of them because there is no junction. Okay. But they have different voltage drops. So the PD across this one will be V1, and then the PD across this one would also be V2. PD will be different. And this is, the PD varies due to this. From Ohm's law, V is equal to IR. So if in a circuit, I is not changing, then we can say that I is a constant. So V is directly proportional to R, meaning when R increases, V1 would also increase. When R2 increases, V2 would increase. Okay. But if R1 is equal to R2, then V1 would also be, sorry, if R1 is equal to R2, then V1 would also be equal to V2. Then in this case, both I and R are constant. They don't vary. And so V1 and V2 would also be the same. Please, is that understood?
Yes, please.
Is there any question? Is there any question? Okay. Ekwe are you there?
Yes.
So in series connection, please, these are the things you must know. In series connection, current flow through the resistors or loads are the same, but voltage varies or potential difference across the loads vary. Now, current flow is equal because there is no junction. Potential difference would vary because the PD is directly proportional to resistance. So when resistance increases, V would also increase. So I will be the same, but V1 and V2 would vary. This is E or V, source voltage. Now, what will be the relation or equation for the total resistance? If we are looking for the combined resistance of all the resistors, what will that be? So, the total or equivalent resistance will be equal to, let's find V1. What do you think will be the expression for V1? If I'm looking for the voltage drop across resistor 1, how do I determine this? Yes. How do I determine V1? I'm waiting for your views. Akuya, how do we calculate V1? Akuya, are you there?
Yes, sir.
I'm listening to you. How do we determine V1?
It is I times R.
Come again.
I times R.
So, yes, current flow through all of them is constant. So V1 will be equal to I times R1. Inshira, how do we determine V2? How do we determine V2?
I times R2.
So I times R2. Now, because this is a closed circuit, you see there's no break. There's no break. The PD across all the resistors, V1, V2, if there's a third one, V3, V4, blah, blah, must be equal to the source voltage. So in a closed circuit, V, which is the source voltage, must be equal to V1 plus V2. Please, if the circuit is not closed, we cannot say that V1 is equal to V is equal to V1 plus V2. This is similar to water flow. If no part of the pipeline, okay, leaks, then we can say that the sum of the water or the volume of water which comes to Josephine's house, which comes to Inshira's house, it must be equal to the volume of water that is pumped from the source. Okay, so what is coming to Josephine's house? What is coming to Inshira's house? When we add, it must be equal to the volume of water that is pumped. But the moment there is a break in the pipeline, you cannot say that what is coming to Josephine's house and Inshira's house will be equal to this. There is a break, so there is leakage. Okay, so this only works when there is a closed circuit. If there is a closed circuit, then the source voltage must be equal to V1 plus V2. If there is other voltages, we'll do that. Okay. So if V is equal to V1 plus V2, then we had V1 as I times R1 plus we also have V2 as I times R2. Therefore, let's factorize out I. R1 plus R2. Let's divide through by I. When you divide through by I, what will be this ratio? What will be this ratio?
R.
So R. So this is equal to, this R is equal to the total resistance, RT. And RT is given by R1 plus R2. It is termed the total resistance or equivalent resistance. What this relation means is that if you have resistors connected in series, the total resistance is equal to the summation, the algebraic sum of all the resistances within the circuit. Are you okay? Hello, are you okay?
No, please.
I said, which part are you not so clear about? Where is it this?
Yes, before that.
We are just
Yes.
We are substituting whatever we had for V1. V1 we had I times R1. Then V2 we had I times R2. So when we factorize out the common term, which is I, we have R1 plus R2. Then we divide through by I. When you divide through by I, that's it. Then you ask, what is this ratio? Voltage over current. Voltage over current, source voltage V over the total current I flowing through would give you RT. So RT is equal to R1 plus R2. What this means is that If I'm looking for total resistance in a circuit, there are two ways to do that. One, add all the resistances within the circuit. Or divide the source voltage by the current flowing through the circuit. So either RT is equal to R1 plus R2, or source voltage divided by source voltage or source EMF divided by the total current. Immaculate, are you okay?
Yes, please. Thank you.
Now I can also play around this same equation. I can play around this and get something else. Maybe I want an expression for V1. Now, from our final equation, we are saying V over I equal to R1 plus R2. Okay. So if V over I is equal to this, help me make I the subject. Oh yeah, help me make I the subject from this equation. Oh yeah, I'm waiting for you. Make I the subject from this equation.
Is I is equal to V over R1 plus R2.
V over R1 plus R2. Substitute this I in place of I here. So V1 will be equal to V over R1 plus R2 times R1. So I can rearrange this beautifully to look like V1 is equal to R1 over R1 plus R2 times V times V. This is another beautiful expression for V1. Please, is that understood? Is that understood?
Yes, please.
Yes,
We can do same for V2. We can do same for V2. V2 is equal to I times R2. And we are saying that source voltage over I is equal to R1 plus R2. So we make I the subject here, which is equal to Vs over R1 plus R2. So if the current I is equal to this, then we substitute I into this equation. V2 therefore becomes V source over R1 plus R2 times R2. Then we rearrange this beautifully. So we have R2 over R1 plus R2 times Vs. So where Vs is the source voltage, this one. All right. Now, so generally, all that we are saying is that when resistors are connected in series, the total resistance is equal to the sum of all the individual resistances, or this is also equal to source voltage divided by current. Divided by current. And please, you must know how to prove this. You must know how to prove this. This is either RT or R equivalent. And what it means is that when resistors are connected in series, if the equivalent or the effective resistance is always greater than any of the individual resistances. Okay, so R1 is this, R2 is this, but the equivalent or the effective resistance is always greater than any of the individual resistances. So what it means, what it also can mean is that if you have two resistors and you want to create a circuit whose total resistance is always greater than any one of them, then connect the resistors in series. Connect the resistors in series. And the total resistance would always be greater than any one of them. All right. Let's look at resistors connected in parallel. Parallel circuit. Then we apply this to solve questions. Then we look at advantages. I'm using 2, but please, it can be more than 2, 3 or more. So if I have 2 resistors or bulbs or loads, look at how to draw parallel connection. Parallel connection is similar to how we used to stand at parade. One person behind the other person. Then, Inshira, you are here. This is Oyabre, I think Josephine. Josephine is here. And then this is Inshira. Inshira is right behind Oye. So the left hand of Inshira is put at the shoulders of Oye. Then the right hand of Oye is put at the shoulders of her as well. So this one becomes resistor 1, resistor 2. Then it is, so we have joined left, right, right. Then the joined right, and then the left, connect to, let's connect to the positive side of it, positive side of the battery. And then The negative side is also connected to the other side. There's a source voltage. This is what happens in parallel connection. This is what happens in parallel connection. So if you have resistors connected in parallel, two resistors, this is one, this is another. Please, in a circuit, a resistor can be drawn as this, or either we represent a resistor as this, or this. So either this one or this one represents, is a symbol for denoting resistance. Or yes, or resistors. Okay. So two resistors connected in parallel will look like this. And then, so this is R1, this is R2. Then each joint side connected to one terminal of the source of EMF, E. The EMF is also the same as the source voltage. Now, when resistors are connected in parallel, what happens is that, you see, over here there is a junction. When you look at this point, or this point, we have three wires. This one, and this one. At this point, we also have this wire, and this wire. So because there is a junction, when the current gets to the junction, it will break. So current always flow from positive terminal to the negative. So it will flow from here. Then when it gets here, it will break into two. Some will go, what is entering the junction is I, but it will break into I1 and I2. So this time around, the current flowing through each one of the resistors vary because there is a junction. They vary because there is a junction. So in
Sir,
hello,
please, if they vary, is it because of, let's say, maybe the position of the first resistor from the wire is longer than the distance is longer, so
so
to
what
pass.
what is important is that it is varied because there is a junction, and a junction is any point where three or more wires connect. So if you look at this point doesn't qualify for a junction because we have two wires. This point also doesn't qualify. This point doesn't qualify. But when we get here, we have 1, 2, 3. 1, 2, 3. So the current flowing through the resistors is varying because there is a junction. That's all.
Yes,
You
please. Thank you.
now resistors when in parallel connection, current vary. Current in each resistor vary, but the potential difference, the PD across this, PD across resistor 1 and PD across resistor 2. This is V2, this is V1. are the same. V1 is equal to V2 and is also equal to voltage source PD. So when resistors are connected in parallel, they have the same potential difference across all of them, but different current. Now, the same PD because, you see, we combine equal parts. This is the left hand of this resistor. This is the right hand of this resistor. This is the left hand of this resistor. This is the right hand. By set connection, we combined left. And then the joints left were connected to one side of the resistor, of the EMF. So whatever this side has is what all this combined side would also have. Let me redraw it again and then explain it once more to you. The reason why they have equal potential difference is that we have these two resistors. In connecting them, we combine this side. Are you there? We combine equal sides. So the left were combined. Then we are also combining right. Okay. So we join left, right. Then this joint left were all connected to one side of the battery. So if positive, then what it means is that whatever this side has is what the left-hand side would also have. So when this is positive, this side would also be positive. This side would also be positive. Then the right sides, which were also joined, are both connected to the negative terminal. So what this terminal has is what you have, what this one will also have. So at the long run, whatever is here is what is going to be here and is what is going to be here because we've joined equal sides and I've given it to one side of the terminals 8. Please, are you okay? Class, I'm asking you, are you okay with that explanation?
Sylvia, please, can you go over my network for some stable?
I said that it is like, this is you, Oye, Josephine. This is Equia. Josephine's, your left-hand side is connected to Equia's left-hand side. Josephine's right-hand side is given to Equia's right-hand side. So I've joined the two of you like this. Now, the combined side is also connected to a source of power, positive. So by doing this, whatever this side has, you have the same. You all have the same. Then the other combined side is also connected to one side of the battery, which is the negative. So by connecting it this way, whatever this side has, you also have it, you have it. So at the long run, whatever this has is what will be here, positive, negative, positive, negative, positive, negative. That's what you have. The same thing is what this one would also have. So when resistors are connected in series, they have equal potential difference or voltage. That is how come V1 is equal to V2 and they are all equal to the source voltage or source EMF. Are you okay?
Yes, please.
But they will have different currents. Different current because there is a junction. And so when the source current gets to the junction, it breaks into what is going into R1 and what is going into R2. But at the long run, I would be equal to I1 plus I2. When we combine what is going into this and what is going into this, they should all be equal to what is entering the junction. Okay, so sum of currents entering a junction must be equal to the sum of currents leaving the junction. This is entering. It must be equal to what is leaving that same junction. And this is what we call as Kirchhoff's first law. Kirchhoff's first law. All right. Now let's derive the equation for the total resistance in parallel connection. When resistors are connected in parallel, what is the equation for the effective or total resistance? So let's only consider two resistors connected as such. So this R1 I said what we are doing is about direct current. So the source must be represented as either a battery, whether dry cell, wet cell, or solar cell. These are sources of DC. So this source has VS as the source current I, when it gets to the junction, breaks into what is coming into R1, I1, and what is coming into R2. If there is a third one, we'll have I3 as well. Now, when resistors are connected in series, they have equal voltage. So the voltage drop across this one, V1, is equal to the voltage drop across this, V2. There is a junction here, but current will not flow through. You understand that later. So we know that in parallel connection, V1 is equal to V2, and they are all equal to the source voltage, Vs. So I want an expression for V1. What will be the expression for V1? Yes. What will be the expression for V1? Anybody can answer. Anybody can answer V1. Don't waste time.
I1 R1.
So V1 will be equal to I1 times R1. What about V2? What about V2?
I2 R2.
So I2 R2. But then the source current I, that is what is coming here. I is what is entering this junction. We have I being equal to current at the junction must be equal to current leaving the junction. So I is equal to I1 plus I2. This I is equal to what is breaking here and what is breaking into this. So if I is equal to I1 plus I2, from this equation, let's make I1 the subject, I2 the subject, and substitute into this equation. Do that and then give me your final results. Make I1 the subject in this equation, I2 the subject in this equation, substitute into this equation, and then give me a simplified final equation after your substitution. Start work. I want the involvement of all of you, so do it. Are you done? Hello, are you done?
Yes.
Okay, give me your final. Okay, give me your final value after the substitution. Okay,
I is equal to
okay, Aduma.
I is equal to V into bracket.
So I is equal to what?
V into bracket.
Uh-huh.
1 on R1 plus 1 on R2.
Okay, Watson, is that what you also got?
Instead, I don't simplify my own like this.
What did you get after your simplification?
I is equal to V out R1 plus R2 on R1 R2.
I is equal to V out and
R1 plus R2 in bracket all over R1 times R2. Instead, the whole thing on R1 plus R2. The V is just multiplying the numerator.
I get you. So this is what you mean. R1 plus R2 times R1 times R2. Okay, let's take it step by step. So I think I asked you to make I1 the subject and substitute it into equation 3. So I will be equal to, if you make I1 the subject here, you have V1 over R1. Okay, V1 over R1 plus
Stop hitting me.
plus
Shame
V
on you.
over R2. But then, because V1 is equal to V2 and they are all equal to the source voltage, we will change this to V. This is V. V1 is equal to V, source V. This is also equal to source V. So you have V factorized out, then 1 on R1 plus 1 on R2. And that is exactly what Equia had. I know you simplified, so I understand what you were doing. So when we divide through by V, I is the current flowing through the source current. V is the source voltage. What is the ratio of the source current to the source voltage? What is I over V? Class, what will be I over V?
1 on R.
So this is equal to 1 over the total resistance, or the equivalent or effective resistance, is equal to 1 on R1 plus 1 on R2. So when resistors are connected in series, in parallel, 1 over the total resistance or the equivalent resistance is equal to 1 over R1 plus 1 over R2, on and on. So if there are 3, 1 over R total or equivalent will be 1 on R1 plus 1 on R2 plus 1 on R3. If they are 4, the same. Okay. If they are 4, the same. So it means you must also understand how to prove this. If you are given 2 resistors connected in parallel that determine their total or equivalent, this is also known as equivalent, R subscript EQ, or R effective. That is equal to this. So master how to prove this.
Hmm? You go to mapping. You go to mapping.
So please, you must master this. Okay. Now, when you see, I said that when resistors are connected in series, the equivalent or the effective resistance is always greater than any of the individual resistances. So what's in series connection, R equivalent or R effective or R total is equal to R1 plus R2. because we are adding these two to determine R equivalent, R total or equivalent or effective will always be greater than R1 and R2. In parallel connection, the total, the effective, the equivalent resistance is always less than any one of the individual resistances. So if you are given a number of resistors, and as an engineer, you are asked to design a circuit so that the total resistance would always be less than one of them, it means you must connect them in parallel, and the resultant or the effective one will always be less than any one of the individual resistors. Okay, let me explain this using example. We have two resistors connected in parallel. R1 is 10 ohm. This is 10 ohm. R2 is 5 ohm. If I'm to calculate the total resistance, because 1 over R total is equal to 1 over R1 plus 1 over R2, 1 over RT or R equivalent, whichever way you want to call it, RT and this one is not. So 1 over, I'm coming. 1 over R total must be equal to 1 over 10 plus 1 over 5. This is equal to 0.1 plus, this is equal to half, 0.2. So 1 over RT is equal to 0.3. Therefore, RT will be equal to 1 divided by 0.3. And what is 1 divided by 0.3? This is 3.333 watt. Now, compare the value of the total resistance to any one of them. You realize that the total resistance is less than each one of them. Okay, so when resistors are connected in parallel, the total or the effective resistance is always less than any one of them. That is what it means. Adwa, are you there?
Yes, please.
Okay. Now, advantages and disadvantages of series and parallel connection. When resistors are connected, resistors or loads are connected in series, equal current flows through all of them, no matter their individual resistances. What I mean is that R1 can be so large, R2 can be so large, and R3, but you won't have what you like. You have what the system plans for you. So when resistors are connected in series, same current would flow through each one of them. So to some extent, it minimizes huge electric costs. Okay. But its disadvantages are greater than its advantages. So same current flow, and so would minimize cost of electric or power usage. Okay. But then its disadvantages is that, you see, we have two resistors connected in series. They are all connected to the source EMF. And so we have equal currents flowing through R1, R2. Because of equal current usage is minimal, no matter the strength of this load and this load. So it will save cost. But the disadvantage is that if you have a lot of gadgets connected in series, example, bulbs. This is one bulb, another bulb. The moment there is a break fault with this one, everything goes off. When this one develops a problem, everything goes off because they are all using the same connection. So when there is a break in one of them, either the wire or the load itself, it disconnects all the other. Okay. So a problem or fault in any one of them, if it is also this, if the fault happened in R2, this one, then this will work, but this will also go off. Already, this has a problem. But the problem, because there's a break in this, it will affect this one too. And only this will be working. So if it is sockets used in our room and you connect them in series, whenever there is a problem with the first one, it affects all the rest. If there is a problem with this is gone, this is gone, and this is also gone. Only this will work. Now, the other disadvantage is that different gadgets Oye, are you there? Different gadgets that require different currents cannot be connected that require different currents to operate, cannot be connected in series. Example, I cannot connect fridge, heater, or kettle in series. We can't connect fridge, heater, air conditioning in series. This is because the fridge, heater, kettle, or the air conditioner, AC, will require different currents for them to operate. But the moment you connect them in series, you are giving them same current, and so they can work. So different gadgets that require different currents to operate with cannot be connected in series. Okay. So a problem in one of them affects the rest. Then different gadgets that would also require different current to operate cannot also be connected in series. Okay. So these are two main disadvantages with set connection. Any question? Let's look at parallel connection. If loads, gadgets, devices are connected in parallel, what are the advantages and disadvantages? Connected to the source, R1, R2. Let me just include another resistor for explanation's sake. So we have three resistors connected as such. Now, over here, because the current from the source, when it gets to the junction, will break into whatever is coming here. This is R3. R1 would have its current. I2, then I3. Look at something. When there is fault with this one, it will not affect R1. Neither will it affect R2. So whenever there is fault here, the current will not come into I2 because there's a fault, but it will break through I1 and then R3, eliminating where there is fault. So it will not affect these two. Equally, when there's a fault in this one, it will also not affect the workability of R1 and R2. It will only eliminate this one. Please, are you okay?
Yes, please.
So under this connection, a fault or problem with any one of the loads does not affect the other. So the socket in our rooms, the modern arrangements or circuiting of sockets in our rooms is by a friend of ring system. Ring system is this one. So that when there is a problem with one of them, it doesn't affect the other socket outlets. Okay. So here a fault with one of them does not affect. Then two. You see, Because different resistors or loads are giving different currents, devices that require different currents can work on this kind of arrangement. So you can connect electric heater, fridge, and air conditioner in parallel, because at the end of it, they will all have their separate currents to work with. Okay. At the end of it, they will all have their separate currents to work with. Okay. The only disadvantage is that such connection will require more current usage, because each and every one, so you must supply larger source currents for the different gadgets to work. Okay, so the power usage at the end of it would be greater in set connection. That's the only disadvantage. So if you are asked to state two advantages, or state advantages and disadvantages of series and parallel connection, this is it. If you have any question, ask. Is there any question? If there is no question, then I will send you questions or problems on series and parallel connection to try your hands on. Okay. So I'll send you snapshots of questions which you'll answer from tomorrow. Okay. All right. So good night to all of you. We'll meet another time. I'm looking at if we can meet on Sunday to make amends with the day we missed. So this is where we'll end today's show. In fact, bye-bye and good night. Yeah. I'll send a recording to the group.